Question 1. A circuit is formed by connecting a resistor between the terminals of a battery of electromotive force 6 volts. The battery has internal resistance. Which statement is correct when 1 coulomb of charge flows around a complete circuit? Right, let's just draw that circuit. So we have the cell that's got some internal resistance, and that's connected to a resistor. Let's say resistance R, and that's resistance small r. This can be representative of the cell with the internal resistance, and the cell has an EMF of 6 volts. We know that some of that will be lost. There'll be lost volts here, equal to IR, due to the internal resistance, and the potential difference across this internal resistor, this resistor will be IR. Let's look at the answers. A. 6 volts is the potential difference across the resistor. That's not true because some of the voltage will be lost volts due to the internal resistance. So there won't be 6 volts available to the resistor. 6 joules of thermal energy is dissipated in the battery. Well, that insinuates that no energy gets to the resistor, so that's not true. 6 joules of chemical energy is transformed in the battery. Yes. 6 joules of thermal energy is dissipated in the resistor. No. So the answer is C. 4 resistors are connected as shown. What is the total resistance between X and Y? So these two here are in a parallel configuration. They are then, once we've worked out what the parallel resistance of these two are, then these two will be in a series configuration. And then once we've worked out what the total resistance of this is, that is in a parallel configuration with the 6 ohm resistor below. So let's start with A, working out what the parallel configuration is. 1 over 8 plus 1 over 8 equals 1 over R. So 2 over 8 is equal to 1 over R. Cross multiply, so R is equal to 4 ohms. So that's for A. Then we'll look at section B, which is the series configuration. So at B we've got 4 ohms plus 2 ohms equals 6 ohms because they are in series. Then we'll look at our configuration C, where we have these two in parallel. So we have 1 over 4. Oh, sorry, not 1 over 4. It's 1 over 6 plus 1 over 6 equals 1 over R. So the total resistance is, so that's 2 over 6 is 3 ohms. 3. What is the definition of electric current? Well, you know this because you know your definitions. We can go straight to C. It is the rate of flow of electric charge. Very simple answer for you. The diagram shows a circuit used to investigate the internal resistance of a cell. The variable resistor R is adjusted and the values of potential difference and current are recorded. Which graph shows the variation of V with I? Now, if you go to your revision note template in the main tutorial, there is a section that says common graphs. And that is not there to torture you. That is there for you to learn the common graphs. And one of the common graphs is the internal resistance graph. The gradient allows us to find the internal resistance, and the intercept allows us to find the EMF. So we are looking for that graph there, and the answer is B. So if you've done your revision notes, as we've talked about, you've looked through your common graphs, that question is very simple. The diagram shows an electric circuit containing a potentiometer of maximum resistance R. The potentiometer is connected in series with a resistor, also of resistance R. The electromotive force of the battery is 6 volts and its internal resistance is negligible. So if we had this up here and they were both the same resistance, then the maximum voltage that could be on the voltmeter would be 3 volts. If we had our connection point there, then the voltage would be 0 volts. So the reading we can get on the voltmeter is between 0 to 3 volts. I don't know if that's been useful. Let's have a look. The slider on the potentiometer is moved from P1 to P2. So at P1 it's going to be 0 volts and at P2 it's going to be 3 volts. Which graph shows the variation of the voltmeter reading with slider distance t? Okay, so it has to start with 0, so it's either C or A, and it has to end at 3, so the answer is C. The circuit shows a negative temperature coefficient thermistor and a 1000 kiloohms fixed resistor connected across a battery. Whenever I see something to do with an NTC thermistor, I always draw the graph just to remind me what the relationship of the graph is. And that'll be in your common graphs section in your revision notes, of course. So whenever I see something about a thermistor, I draw that graph. The battery has an electromotive force of 12 volts and negligible internal resistance. Define electromotive force. We'll write it here. Total energy per unit charge made available by the chemical reaction in the battery. You can learn that with me in the mini tutorial in topic 5. There's a mini tutorial called EMF and potential difference. I recommend you head to that tutorial if you don't know that definition. It talks about the theory behind the definition, and you learn the definition with me. State how the EMF of the battery can be measured. I'm wondering if it's a trick question. It's very simple. So the battery has no internal resistance. Therefore, simply place a voltmeter in parallel with the battery. This question is about a thermistor circuit. The circuit shows a negative temperature coefficient thermistor. So remember, we always do this when we see that. And a 1000 kiloohm fixed resistor connected across a battery. The battery has an electromotive force of 12 volts and has a negligible internal resistance. Define electromotive force. We've already done that, folks. You can see that's come up twice already, so definitely something you want to learn. The graph below shows the variation with temperature T. Oh, there's our thermistor graph of the resistance X of the thermistor. Determine the temperature of X when the potential difference across R is 4.5. So if the potential difference across R is 4.5, that means the potential difference across X must be 7.5, because 12 volts has to be split out between the two components, and there's negligible internal resistance. The resistance of the thermistor at that point must be that ratio bigger. So let's just work that out. So the resistance of X is equal to 166.6 kiloohms. So we go to 166.6, so that's 150, 160, 170. Head down. That's 32, 34, 36, 38. So we're going to go with 37. So determine the temperature of X when the potential difference across R is 4.5. The temperature of X is 37 minus 37 degrees centigrade. State the range of temperatures for which the change in resistance of the thermistor is most sensitive to changes in the temperature. So what they're really saying is where is the gradient the steepest? Where are we going to get the biggest change over the smallest temperature range? And we're definitely going to start here. That's very steep. It gets very steep and then it stops being steep around there. And sort of evens off. So I would say the temperature range is minus 50. That's what point number 1 is, and that's point number 2. Oops. So minus 50 at the smaller end, up to, and what we're saying here, yeah, let's say minus 25. That's where we get the greatest change in gradient of the temperature change and resistance change. State and explain the effect of a decrease in temperature on the ratio V across X over V across R. So a decrease in temperature, as my pencil's running out of battery, as temperature, give me a sec. As temperature decreases, resistance increases across the thermistor. Is that right? Yep. That means, therefore, the voltage across X increases, and the ratio of Vx over V over R increases also. A 24 ohm resistor is made from a conducting wire. The diameter of the wire is 0.3 millimeters. Again, that diameter, we usually use a radius, so we're probably going to have to convert that to radius at some stage. Has a resistivity of 1.7 times 10 to the minus 8 ohm meters. I calculate the length of the wire. So we'll go down here, number 1, and we're going to use the formula rho equals RA over L, which you can get from your data booklet. That's the only formula I know that would be useful using the term of resistivity. And we want to rejig that for L. So L equals RA over rho. R is 24. A is the cross-sectional area of the wire. So it's pi r squared. Now R is 0.3 times 10 to the minus 3, that brings it into meters, divided by 2, because we're getting a diameter there, and we square that, divided by the resistivity, which is 1.7 times 10 to the minus 8 rho m. And our solution, let me get my calculator out, is 99.7 meters. Now, how many significant figures are we going to give this to? I think it's okay to leave it at that. That's fine. Okay, so that's point 1. 11D point 2. On the axis, draw a graph to show how the resistance of the wire in D1 varies with diameter. So how does resistance vary with diameter when the length is constant? A data point has already been admitted. So let's go back to point 2. Let's have a think. So we want resistance R equals rho L over A. Length is constant, resistivity is constant, so let's just say R is proportional to 1 over A, and 1 over A, so R is proportional to 1 over R squared. So our graph is going to show 1 over R squared, and we can say R squared is the same as diameter squared because it's just a constant that separates them. So we're going to have a look like this. It's going to go through that point. It's going to be a curve, and it's going to be asymptotic at the axis. And there's our answer there. 11E. The 24 ohm resistor is covered in an insulating material. Explain the reasons for the differences between the electrical properties of the insulating material and the electrical properties of the wire. So we have to say what the differences are. So insulating material does not conduct wire. Oh, can I start that one again? Can you just give me a sec? Because I wasn't speaking any sense there, right? Okay, we want 3 marks. 1. Insulating material does not conduct electricity. Okay. Conducting material does, or the wires do. Wires are made of conducting materials which contain free electrons and allow a flow of charge. Insulating materials have much fewer, in many cases, free electrons or charges available. So no flow of charge. Have we answered the question? Explain the reasons for, that's the reasons why, and yeah, good, done that right. 11F. An electric current consists of a supply connected to a 24 ohm resistor in parallel with a variable resistor of resistance R. So let's call it R2, and we don't know what that is. The supply has an EMF of 12 volts and an internal resistor, so a small r, of 11 ohms. The power supplies deliver maximum power to an external circuit when the resistance of the external circuit equals the internal resistance of the power supply. So that means that the total resistance of this one here, R1 and R2, must equal the internal resistance of 11 ohms. So question 1 says, determine the value of R for this circuit at which maximum power is determined. So we want the total resistance of the circuit, which is in parallel, 1 over RT. Oops. That's our formula for resistors in parallel. We want to find out what the value of R2 is when RT is equal to 11. So 1 over 11 equals 1 over 24 plus 1 over R2. So to find that, we say 1 over R2 equals 1 over 11 minus 1 over 24. And we pop that into our calculator. That gives us 13 over 264. So R2 is equal to 264 divided by 13. It's the reciprocal of that, which gives us a value of 20.3 ohms. Here's our answer. Question 2. Calculate the reading on the voltmeter for the value R you determined in 1. So we want to find out what V is. And I think we're going to have to use E equals I R plus R to find out what the current around the circuit is at that stage. So I equals, these are the equations for internal resistance. E over R plus R, which is 12 divided by 11 plus 11. So that's 12 divided by 22. So the current at that stage is 0.54 recurring amps. My pen's not doing a great job. And then, so V equals IR, so that's 0.54 times 11, which gives us a value of 6 volts. And finally, question 3 says calculate the total power dissipated in the circuit when maximum power is delivered to the external circuit. So P equals V squared over R. We're going to pop the total voltage in, which is 12. I'm going to put the total resistance in, which is 11 plus 11, because the resistance of the external circuit is 11, but that's in series with the internal resistor, which is 11, so it's 22. So 12 squared divided by 22 gives us a value of 6.54 watts. And there is our answers. A resistor X of resistance R is made of length L and cross-sectional A. So let's just write all this down. Resistance X, length X, area X, and it's got the same material, which means the resistivity is the same as Y. So Y is a different resistor, but it has, we don't know what the resistance of that is, but we know it's got, the length of Y is equal to 4 times the length of X. We know the area of Y is equal to 2 times the area of X, and the resistivity is the same because it's the same material. So the resistance of X is equal to rho L over A, and that's all X. And the resistance of Y is equal to rho Ly, which is equal to 4 Lx, over 2Ax. So it means that the resistance of Y is equal to 2 rho Lx over Ax. So the resistance of Y is equal to 2 Rx. Okay, so it says in here X and Y are connected in series. So what is the total resistance of the combination? So the resistance of total is equal to Rx plus Ry. So that's R plus 2R, which gives us 3R. So the answer is C. Each cell in the module has an EMF of 0.75 volts and an internal resistance of 1.8 ohms. So what we've got here is we've got an array of cells or batteries all added together, and they're added in 2 ways. They're added together in series on each branch, and then there's 3 branches of parallel. They're added together that way. Okay, so what we'd usually be looking at is resistors in some sort of arrangement like this, but instead we're flipping it around and saying let's look at cells arranged like that. But the rules still apply. So calculate the EMF of the module. What we have here is each of these little cells has 7.75 volts. So in series, we'd add them all up. So in this branch alone, that would be 3 volts. And in this branch, it would be 3 volts. And in this branch, it would be 3 volts. But because these branches are in parallel, we're only interested in the voltage across that one branch. And then each branch gives that same voltage of 3 volts. So the total EMF of the module is actually 3 volts. So the answer to question 1 is 3 volts. Okay, EMF is equal to 3 volts. Determine the internal resistance of the module. So what we're looking at is the total resistance of this module. You can see that we've got 4 cells, each with their own resistance of 1.8 ohms in series. So to find out what the total resistance of this array of series, we do RT equals 1.8 plus 1.8 plus 1.8 plus 1.8, which gives us 7.2 ohms. But we're not finished there because that whole branch is 7.2 ohms, which is in parallel with this whole branch, which is 7.2 ohms, which is in parallel with this whole branch, which is 7.2 ohms. So the total resistance we've got to look at in parallel. So 1 over 7.2 plus 1 over 7.2 plus 1 over 7.2 gives us 3 over 7.2. So RT equals 7.2 over 3, because we're just swapping around. And that gives us a value of 2.4 ohms. So the total resistance of that cell, that module, is 2.4 ohms, and that equals the internal resistance. All right, so the internal resistance, we'll give that a small r, is equal to 2.4 ohms. The diagram below shows the module connected to the load resistor of the, so there's a big resistor, big R, a load resistor of 2.2 ohms, and we want to know what the power dissipated in that load resistor is. So to find out the power dissipated, we see P equals I squared R, and to do that, we know what R is, but we want to find out what I is. So we're going to use the equation for internal resistance, using internal resistance, EMF and internal resistance. You can probably find that in the data booklet. Okay, so we know 3 is equal to I, so we want to find R plus R, so 2.4 plus 2.2. So I equals 3 over 4.6, which gives us a value of 3 divided by 1.6. 0.65 amps. We want to square that because P equals I squared R, and then times by 2.2 because that's the resistance of the load resistor. So the value comes out at, I'm going to go up this way here, P equals I squared R, so it's 0.65 squared times 2.2, which gives us 0.935. Let's round it down to two significant figures, 0.94 watts. Yeah, so that's the power dissipated in the load resistor. Discuss the benefits of having cells combined in series and parallel with the module. Okay, so you can see that adding in series along here means that you can increase, series means that you can increase the value of the EMF. So you could make it, you could keep adding 0.75, so you can make it a 6 volt module, or you can make it a 9 volt module or 10.5 volt module. So the reason it's in series is it means you can increase the value of the EMF. Having it in parallel, you can see when you add resistors in parallel or resistances in parallel, the resistance ultimately decreases. So if you have it in parallel, what that means is the internal resistance of the module or the power source decreases, which means you're dissipating less power inside the module than you are if it wasn't in parallel. The other good thing is, say this one breaks, well, the module still works. You're still giving out 3 volts or 6 volts or however many cells you put in parallel in series with each other. It's just mean that branch doesn't work, which means the resistance goes up, but the module still works. So 3 reasons. Series is good because you can increase the value of the EMF of the module. Parallel is good because you decrease the internal resistance of the module, which means you dissipate less wasted power through the internal resistance. And if one of the modules or the EMF, cells, loses power or breaks, but the module will still give out the same value of EMF. Each of the resistors in the circuit has a resistance of 2 ohms, and the cell has an EMF of 3 volts and negligible internal resistance. The ammeter has negligible resistance. What is the ammeter reading? Okay, so we need to work out the total resistance of the circuit. There's 2 parallel branches, so 1 over RT equals 1 over R1 plus 1 over R2. The total resistance of branch 1, which is this branch here, is 6, so 1 over 6, and then the total resistance of this branch 2, which is this branch here, is 2, so 1 over 2. 1 over 6 plus 3 over 6, try and add fractions, so 1 over RT is equal to 4 over 6, so RT is equal to 6 over 4, so we're just swapping that round. That gives us the total resistance of the circuit is 1.5 ohms. Now the total current of the circuit is therefore I equals V over R. So it's 3 over 1.5, which gives us 2 amps. So at this point here is 2 amps. At this point here it's 2 amps. But at these points, branch 1 and 2, it splits up. And in branch 1, we expect the current here to be smaller than the current there, because the resistance is higher. And we expect it to be smaller by a factor of 3. Okay? So if we say in branch 2, we have 1.5 amps, then to make it up to 2 amps, that could be 0.5 amps. And that is 3 times smaller than branch 1. So that all works out. So the answer is C. The graph shows the voltage current characteristics at a constant temperature of 2 electrical components, X and Y, outlined with reference to the graph and Ohm's law, whether or not each component is ohmic. So it'll be 1 point for stating what Ohm's law is, 2nd point for looking at X to see if it's ohmic, and the 3rd point for looking at Y to see if it's ohmic. And Ohm's law is that voltage across a component is directly proportional to current through the component, and it's really important to write at a constant temperature. My writing is dreadful, sorry. Okay, so that's mark number 1. Looking at X, you can see that it is directly proportional because it's a straight line through 0. So X is an ohmic conductor because V is proportional to I because it goes through 0 and it's a straight line. Okay, you can see that Y is not an ohmic conductor. Oh my, I'm so sorry about my writing. That's because V is not proportional to I. It does go through 0, 0, but it's not a straight line. Okay, so that's the reasoning behind it. I wouldn't give my answer to the examiner like that. You'd have to make it a bit clearer. Components X and Y are calculated in parallel. The parallel combination is then connected in series with a variable resistor R and a cell of EMF 8 volts with negligible internal resistance. That's quite good. It means we don't have to consider internal resistance. The resistance of R is adjusted until the currents in X and Y are equal. Use the graph, calculate the resistance of the parallel combination of X and Y. So go back to the graph, and you would remember we had that situation there with the graph. I don't want to go back to the graph now because it'd be too annoying. So at this point here, that was current, that was voltage. That point there is where the current is the same in each, and it says on the graph that that point is 4 milliamps. So there's 4 milliamps going through at that stage, 4 milliamps going through at that stage. And if we look at the voltage of each of them, the voltage of each of those at that stage is 6 volts. So that means that this chunk here is getting 6 volts of the EMF, which means that chunk there is getting 2 volts of the EMF. Okay, so we can use this information to calculate what the resistance of that is, right? So R equals V over I. So voltage is 6. The current is 4 times 10 to the minus 3 amps, which gives us 1,500 ohms. So the resistance of X is 1,500. Given that resistor Y is exactly the same, the resistor of Y is 1,500. And we want to know the parallel combination of R and Y. So 1 over RT equals 1 over Rx plus 1 over Ry. So that's 1 over 1,500 plus 1 over 1,500 equals 2 over 1,500. So RT is equal to 1,500 divided by 2, which gives us 750 ohms. So the answer to number 1 is 750 ohms. Using your answer to E, determine the resistance of R. So big R, we know has a voltage of 2, and we know it's also got a current of 8 milliamps, because there's 4 coming from here, there's 4 coming from here, they add up to 8. So we've got 2 over 8 times 10 to the minus 3 gives us a value of 250 ohms. So that's the answer to number 2. Determine the power delivered to the cell by the circuit. So power is equal to I squared R. I squared is 8 times 10 to the minus 3. That's the whole power of the circuit squared. Times the total resistance of the circuit. Total resistance of the circuit is 750 plus 250. So gives us a value of 0.064 watts, which is 64 milliwatts. And that's the answer to number 3. Question 13. The graph shows a variation of current I in a device with a potential difference V across it. And we've got a graph here, and it says, what is the resistance of the device at P? Okay, this is a really simple question, but I'm going to explain to you why it's quite difficult. R equals V over I, V is 20, and I is 2. So our resistance is 10 ohms, and the answer is C. Why is it difficult? Well, lots of students, including myself when I was younger, believed that the resistance is equal to the gradient of the graph. And the resistance would be the gradient of a VI graph. And if that was the case, the gradient would be infinite and the answer would be D. But this is not true. This is simply not true. Resistance is not the gradient of the graph. Resistance is only found by this equation here. It's a point on the graph taking the values of voltage and current at that point. So your answer to question 13 is C. And a very important lesson to learn here and to remember is always use that equation to find the resistance of a component. Don't be tempted to use the gradient of the graph. Question 14. A circuit consists of a cell of electromotive force, 6 volts, and negligible internal resistance, brilliant, connected to 2 resistors of 4 ohms. The resistance of ammeter is 1 ohm. What is the reading of the ammeter? Well, worth noting, if the resistance of the ammeter is 1 ohm, it's not an ideal ammeter. And this is just for knowledge, really. An ideal ammeter has 0 resistance, and it doesn't take a share of potential difference. That's just for notes, really. It's not going to answer this question. Okay, what is the reading of the ammeter? We want to find out what the current through the ammeter is. We know that this is 1 ohm, and we can work out what the total resistance of this parallel structure is here. RT equals 1 over 4 plus 1 over 4, which is of course 2 over 4, which is 1 over 2. So RT is then equal to 2 ohms. That means that this structure here takes 2/3 of the share of the voltage, and the ammeter takes 1/3 of the share of the voltage. So the ammeter gets 2 volts. What does that tell us about the reading of the ammeter? Well, I is equal to V over R. 2 divided by 1 gives us 2 amps. The answer is A. Question 15. In an experiment, a student constructs the circuit shown in the diagram. The ammeter and the voltmeter are assumed to be ideal. Great. State what is meant by an ideal voltmeter. Okay, well, we've just talked about what an ideal ammeter is. An ideal voltmeter is one that has infinite resistance. Ooh, why can't I write resistance? Let's try again. So instead of 0 resistance, which the ideal ammeter had, this ideal voltmeter has infinite resistance, and it does not draw any current. Remember that our ideal ammeter did not take a share of the PD. The ideal voltmeter does not draw any current. The student adjusts the variable resistor and takes reading from the ammeter and voltmeter. The graph shows the variation of voltmeter V with the ammeter reading I. Whenever I see a VI graph and I see this shape, I automatically think of internal resistance. This is the classic internal resistance graph. The y-intercept is the EMF and the gradient is the internal resistance. So let's see what the next question is. Use the graph to determine the electromotive force of the cell and the internal resistance of the cell. Okay, so let's find out what the EMF is. It is the y-intercept. We're going to go up and have a look at it here. I would say we are looking at pretty much halfway between those 2 points actually. So I'm going to say that's 9.0 volts. Okay, now we want to find the internal resistance. So we're going to use the gradient of the graph. So let's draw ourselves a big gradient triangle. And our change in y, let's start with change in x. Our change in x is 4.8 minus 0.2, which is of course 4.6. And our change in y is equal to 8.8, I'd say, because each of these is 0.4. So that's 8.8. So 8.8 take away 5.2, which is 3.6. Now to find the gradient, we do change in y over the change in x, which is 3.6 divided by 4.6, which gives us an answer of 0.78. And that's going to be ohms. Let's put that down to one significant figure. 0.8 ohms. Let's put them in the right place. Electromotive force is the y-intercept. I'm just telling the examiner I know my stuff, and we decided that would be 9.0 volts. And the internal resistance of the cell is the gradient, which gives us 0.80 ohms. Question 16. A 12 volt battery has an internal resistance of 2 ohms. So we've got EMF is equal to 12 volts, R is equal to 2 ohms. A load of variable resistance is connected across the battery and adjusted to have a resistance equal to that of the internal resistance. What statement is correct for this circuit? I'm just going to draw the circuit quickly. I just find it easier to visualise when I've got it all written down. 2 ohms as well, and we've got 12 there. The current in the battery is 6 amps. Okay, well let's have a look at that. E equals I R plus R. I is equal to 12 over 4. So our current is 3 amps. Not true. The potential difference across the load is 12 volts. Well, we know that that's automatically not true because some of the potential difference will be lost volts here, and it's going to be the same lost volts as across the load at this stage because they have the same resistance. So this is going to be 6 volts, and there's going to be 6 volts lost in the battery, so that's not true. The power dissipated in the battery is 18 watts. Well, P equals I squared R. I squared, well, the current going through the battery is 3 amps times R, which is 2. So we've got 9 times 2, which is 18. I believe that to be correct, but let's just check the last one. The resistance in the circuit is 1 ohm. Well, no, the resistance in the circuit is not 1 ohm. The resistance in the circuit is 4 ohms. Answer C. Question 17. The graph shows how current I varies with potential difference V for a resistor R and a non-ohmic component T. Okay, well the gradient of this graph is constant, which tells us that any time we make this calculation it will also be constant. So we're looking at a constant resistance here for resistor R. That's not the case for T. If you complete a calculation at any point, so for example here, R1, or RT1, and say here, RT2, they would be different. And for that reason, this is a non-ohmic conductor. What's the question? 8.1. State how the resistance of T varies with current going through T. Okay, well let's just work out what our T1 is. It's V over I, which is 1 over 0.02, which is 50 ohms. And RT2 is equal to, I'm going to draw a non-straight line without a ruler. Don't you do this. I just can't bother getting the ruler out. Okay, so RT2 is 6.8 divided by 0.66, which gives us a value of, well, it's going to be greater than 10, isn't it? 10.3 ohms. We can see that the resistance has decreased. So as current increases, resistance decreases. 8.2. Deduce without a numerical calculation whether R or T has the greater resistance at I equals 0.4. Okay, well R equals V over I. I'm not going to make any calculations, don't worry. But this is the same. This is constant for both at this point here. I'm going to just tidy this graph up a little bit. Give me a sec. Okay, at 0.4, it's got the same current, but the voltage of T is here, and the voltage of R is here. So R has a greater voltage at that point. And if R has a greater voltage than T at that point, then the resistance of R is going to be greater than the resistance of T because of that calculation. So the answer is 1, resistance of R is greater than the resistance of T, because 2, for the second mark, the current through each resistor is the same. But the voltage across R is greater than that across T. It's worth noting again, and I'm going to actually draw this in red. The mark theme says ignore reference to gradient. Okay, we do not like talking about gradient when we're talking about the resistance and a VI graph. B. Components R and T are placed in a circuit. Both meters are ideal. Slider Z of the potentiometer is moved from Y to X. State what happens to the magnitude of the current in the ammeter. I'm going to take a rather long answer to this, and I'm going to use some values. I want you to imagine this is a sliding scale, and when Z is here, the resistance of XY is 10 ohms, and when Z is here, the resistance of ZY is 2 ohms. Okay, so let's look at when we've got the 10 ohms situation. The total resistance of that whole circuit then, it's a parallel circuit at that point, isn't it? So we've got 1 over 10, which is this one, plus 1 over 2 plus 1 over 2, which gives us 1 over 10 plus 2 over 2, which is 1 of course, which gives us 1 over 10 plus 10 over 10, which gives us 11 over 10. So the total resistance of that whole circuit is 10 over 11, which is 0.9.
ohms. So when the Z is here, the total resistance of the whole circuit is 0.9 ohms. Now let's look at what happens when Z is here. Do the same calculation. There is going to be a parallel element because there's 2 ohms here, and then there's the 2 ohms and the 2 ohms, and they're all in parallel with each other. And then what we have is, it's like the rest of that 8 ohms is in series with that parallel circuit. So to find out the total resistance of the circuit, we do 1 over RT equals 1 over 2 plus 1 over 2 plus 1 over 2, which gives us 3 over 2. So the total resistance of the parallel component is 3 over 2, which is 1.5 ohms, but also it's in series with this extra 8 ohms. So the total resistance of the whole circuit is 9.5 ohms. So you can see that as the slider moves from Y to X, the resistance of the total circuit increases. If the resistance of the total circuit increases, then the current of the total circuit decreases. And that means that the current on A, which is part of this circuit, must also decrease. So state what happens to the magnitude of the current in the ammeter. It decreases. That question actually for 1 mark was quite hard because it is asking you to make an understanding of how the total resistance of the whole circuit would change without doing any calculations. And actually my little brain, well, actually I'm not going to downplay myself, I've got quite a big brain actually. My brain preferred a calculation on that point, so that's why I did that. Didn't make it easy to get the marks, mind you. And finally, B2. Estimate with an explanation the voltmeter reading when the ammeter reads 0.2 amps. So when the ammeter reads 0.2 amps here, that means that the current of R plus the current of T both equal, added together, 0.2. So IR plus IT equals 0.2 amps. Let's go back to our graph and see how easy that would be to find out. So we need to find out a point, a voltage, and it's got quite a small voltage I would say, where both of these currents add up to 0.2. So we know it's within this range here. Actually, we kind of know it's actually within this range, don't we? Because the current here, let's say at 1, I'm going to do this in green so it's easy for you to see. The current at this point is 0.02 plus 0.07, so that makes 0.09, so it's not that. So let's go to 2. The current here is 0.06, and the current here is 0.14. Oh, wait a minute, if you add 0.14 plus 0.06, that actually gives us 0.2. Okay, so at that point, both currents add to 0 and our voltage is 2. So the voltage across these two must be 2 volts. The answer is 2 volts, and it says with an explanation. We're going to get 1 mark for that and the 2nd mark for the explanation. And it has to be this, they have to have the same voltage across them. So the resistors are in parallel. Each branch gets the same voltage. The currents through each resistor must add to 0.2 amps. And I think I am done.